Hello, this is Jason Kendall and welcome to the next of my introductory astronomy lectures. Today we're continuing on the history of the atom, where we talked last time about what an atom is, what elements are, how they have protons and electrons and neutrons, and how they're arranged in these orbits around them, and there's isotopes and so forth. But where did this concept of the idea of the atom ever really come from? So that's what we're going to talk about right now. So the history of the atom is an interesting one because it develops out of natural philosophy. Natural philosophy is basically a way of talking about the world, philosophizing about the world in a way that is consistent with how you perceive the world. And so natural philosophy is a way of conducting science without having the tools to actually be able to gather the evidence or analyze it, but you do it as rigorously as you can. So let's take a couple of ideas about the nature of what we mean by matter, because stuff is in existence, and so stuff does things to other stuff. So you might want to say, well, what exactly is matter? And some of the earliest recorded ideas about what the nature of matter are come from Democritus, who was a pre-Socratic philosopher in ancient Greece, and his goals around 400 BC or so, thereabouts. He came up with the concept of an indivisible unit of matter. Meaning you can cut something and keep cutting things and it doesn't divide. And that's where the word atom comes from. Atomos, meaning not divisible, not cuttable, not sliceable. That's what tomos, meaning to cut or divide, a meaning not. So the atom is that which cannot be cut. Democritus himself is referenced throughout much of antiquity's literature. However, a lot of his works do not survive because he was kind of on the outs with respect to medieval theology, and he disagreed with Plato and Aristotle and some key ideas, so his work was excluded throughout history. But we know that he came up with that he alluded to the concept of the atom. We also know that he alluded to the idea that the Milky Way is a series of stars that are incredibly distant, that they're so distant that they actually look like one thing. And that kind of it goes along with this concept of the atom. And let's see what that is right now. The concept of the atom that Democritus had is that imagine you had a block of clay, or anything, but let's just use clay for this instance. Actually, I'm going to diverge away from it. I'm not going to say clay, I'm going to start with a tree. And if we start with a tree, and you cut the tree, say, in half, well, which half of the tree is it? Well, you know, you're going to get some half, whatever it happens to be. Let's say we cut it vertically. And so you've got a half of the tree that's vertically cut, and so it still has a big chunk of the branches, a big chunk of the root, and a big chunk of the leaves, and so forth. But at some point, as you keep cutting this tree in half, depending on how you cut it, eventually you're going to have to get to a point where you're going to cut the tree and you're going to divide the bark or the wood of the tree from the leaves of the tree. So therefore, the tree was one thing. And now you're cutting into two things, and each of those things is different from the other. All right, so now you're paring away the thing that is not the same as it. So we get rid of the leaf, and so we're left with the wood. And so now we cut the wood away, and we say, oh, there's the meat of the wood that's below the bark, and we have the wood that's above the bark wood, and so we cut away the bark. And now we're left with the wood which has the grains, and it's that nice yellow tone. As we cut further, we find that there's water inside of the bark. We find that there's inside of the wood. We find that there's sap inside of the wood. We find that there's dark and light little striations of the wood. So we keep cutting those things, eliminating the bark, eliminating the sap, eliminating the water, trying to get down to the essence of what is wood. And so at some point, you can philosophize that you would get down to the point where you say, I've cut away everything that is not wood, and I found the tiniest element of something that is wood, and if I cut it, I will no longer have wood. I might have something else, but then I just keep cutting until I get down to the thing that I say that this is the element of wood. So the concept of the atomos then says there must be some fundamental building block out of which you can no longer cut, because how can you cut anything infinitely, posed Democritus. And so this is an interesting concept. Likewise, that's where his concept of matter comes from. It doesn't matter whether it's clay or water or anything. There will eventually be some point at which you cannot cut any further, because that is the atomos, the indivisible unit. Well, this has some ramifications, and there was no real evidence for it because, like I said, in 400 BC, it's philosophy, it's not science yet. So the thing is that other philosophers disagreed, notably Plato and Aristotle, who disagreed with him entirely, and thought that matter, like space, is continuous. So you'll notice that there is no gap in space or gap in matter between, say, the tree and the air that surrounds it, or when the tree is submerged in water, the water goes right up to the tree, so there must be a transition between tree and water. Now, it's a very sharp transition, but we notice that there's water in the tree, that the sap is made from tree and water, that when you burn a tree, the fire comes out of the tree. And so it's very interesting to think that maybe a tree is made up of fire, maybe it's made out of some sort of earthy element, maybe it's made out of some sort of airy element because the fire lifts, the smoke is lifted out of there. Maybe it's made out of some sort of water, well, we know that. So all of these things can combine together, and if you combine them in just the right way alchemically, an alchemist would do this, then you would get tree. So the proper combinations of fire, earth, water, and air, according to Plato and Aristotle, give you tree, or gold, or iron, or what have you. All of the various things that exist, according to Plato and Aristotle, were continuous matter, and this continuous matter can never be subdivided, and you can't find a boundary to it. So it's kind of innately linked to the concept of space as well. So why did Aristotle disagree, and what happened, and where did the concept of this continuous matter, and how did Aristotle blast Democritus' idea? Well, he appealed to religion and appealed to divinity. And divinity is definitely a part of natural philosophy, and you can actually add it in by saying, imagine that there's a spiritual plane, a spiritual divine plane, and this was okay in that time because they divided the physics of the earth, the materia, versus the physics of the heavens, the celestia. And the two really did not behave the same according to anybody's observations. So the celestial realm is the divine realm. It's the unchanging realm. It's the permanent realm. The material world is ever changing and ever fluid. And so there is a concept which arises from the four elements, and the fifth element is then spirituality or divinity. And Aristotle said the following: so, Mr. Democritus, you're saying that the god Zeus, who is all-powerful, who took the eight-legged beast and ripped it apart to make man and woman, you're saying that he cannot rip apart the tiniest dust mote, the thing that you say is the smallest possible thing? How can a god not break that apart? And that's kind of a valid philosophical argument if you posit the existence of deities. So it really is a big thing, and so most of Christian thought and most of Western thought gravitated towards the concept of the continuous matter in Aristotle's thinking because of the heightened element of the divine in natural philosophy. All right, so it took some time before people would take Democritus's idea seriously, and John Dalton in about 1803 or so, 2,000 years after Democritus came up with this concept, 2,000 years, and even 200 years after Galileo first put some dents in the armor of Aristotle with all of his work, so then we have Dalton coming along and proposed, well, we've got some interesting things that we see. We see that if you have water is always not roughly 88% or 88.9% mass oxygen, and the rest is hydrogen. So we can always have that the same, where the percentages of oxygen and hydrogen are always the same, where mass is conserved and mass doesn't disappear or reappear. You can say, well, imagine that there's little tiny building blocks that have certain amounts of mass, and these things then, matter then is the arrangement of these little tiny building blocks. And perhaps some of those little tiny building blocks are hydrogen, some of them are oxygen, and it's a process of discovering which they are. And so the atomic theory that Dalton revived, he used the word atom, atomic theory, he said that atoms can neither be created nor they can be destroyed, they are just there, they're pieces of matter that are permanent in existence, and all chemistry can be defined by adding and putting together various atoms in various arrangements. So the Dalton's theory of the atom, which is which is a highly simplified version of chemistry today, is that basically, well, even when you do elementary first semester chemistry, you're going to be looking at Dalton's version of the atom. You're not going to look at quantum mechanics just yet. But when you look at Dalton's version, you say, well, if you want to make water, well, you take one atom of oxygen and two atoms of hydrogen, and that is water. And if you want to make carbon dioxide, it's one carbon and two oxygens. If you wish to make methane, it's CH4. And if you want to make ammonia, it's NH3. So you got all these things where they combine together, and the combination thereof becomes the molecule. So Dalton's theory of the atom worked out pretty good. Every element has its own particular properties. They all have the same properties, and atoms simply combine in whole numbers. You can't break atoms apart in order to say, oh, there's no half water, which is like a half an oxygen and one hydrogen. That's not half water. There's no such thing as half water. So Dalton's idea of the atom held sway for about 100 years. And about 1903, roughly actually more like 1897, Sir J.J. Thomson discovered the electron, the first fundamental particle. This is the discovery of the concept that yes, there can actually be fundamental particles, meaning things that cannot be divided anymore. The literal Atomos of Democritus back in 400 BC. So what he discovered was the electron, which had a negative charge, and it must reside. He discovered it by using cathode ray and understanding what the nature of a cathode ray is. And so what he said is that, well, wait a second, we know these electrons must exist. And so he posited then that perhaps Dalton's concept of the atom can be modified. Instead of being this smooth distribution of Lego blocks or just little things, little balls, like billiard balls that are smooth, perhaps inside the billiard ball of Dalton, there are electrons, and they're moving around. And so therefore, if there's an electron, which is a negative charge, there must be some positive charged object, a proton, that's also in there, because every atom is electrically neutral. If it wasn't, it would be quickly therefore. It would quickly neutralize itself by either acquiring an electron or losing an electron. So Thomson's concept is that inside of each of these little billiard balls, Dalton's billiard balls, there were a plum pudding of electrons and protons in a mash that neutralized themselves out. So this is a good little model of the atom. And the thing is that it took the concept of the electron and said, oh, it's a piece of the atom, and inside the atom there's this thing. All right, so this also led him to learn that electrons were about 2,000 times smaller mass than the proton. Whatever it was, these tiny, tiny, tiny things were there. Anyway, so it didn't take long for people to say, well, okay, got it. What Thomson is saying is that the electrons and protons are arranged inside the atom. All right, how exactly are they arranged? That's a really key question. It's like, okay, fine. Are they moving randomly? Do they have structure? Are they set up like little bricks? How are they set up inside of Dalton's little atom, and into how is the plum pudding mixed? Are the plums evenly distributed in the pudding, or are the plums tiny little bits going through? So what Sir Ernest Rutherford in 1911 sought to understand this, the interior of Thomson's plum pudding model, and what he decided to do is to say, I'm going to take a very, very, very heavy atom that I can make into a very, very, very flat sheet, an extraordinarily thin, flat sheet. And the goal of this extraordinarily thin, flat sheet is that if I throw something at a thin, flat sheet, things should go through it or bounce off of it. And you know that if you take an object that is not flat and you throw something at it, things can reflect off of it in all sorts of ways. So if you take a flat surface, then you bounce a ball off of the flat surface, the angle of incidence equals the angle of reflection off of a flat surface. However, if the surface is all jagged or regular in some way, then if you throw balls at that surface at different angles, the angle of incidence at the location where the ball hit the surface, let's say you do this off a basketball court, which is flat, and now you play a game where it's on a curved surface like this, maybe it's got humps, and so as it reflects, you can actually see where it reflects from and where it goes to after it reflects, and that gives you a map by looking back where the things came from is to the shape of the object. And now that's one way of looking at things. But Sir Ernest Rutherford, why do I keep saying sir? I forget if he is a sir. In any event, Ernest Rutherford in 1911 said, I'm going to take gold, which I can hammer down and make into gold foil. And this gold foil can be literally only a few atoms thick, just the thinnest thing. And this is an amazing property of gold, by the way. And gold itself can be made into very, very thin foils. And it's so thin that if a gold atom is one of Thomson's plum pudding models, then the electrons in there have to be distributed in some way. And if I throw something at it and it goes through the atom, it might deflect it as it goes through. So if you throw something through something, go through something and you interact with it gently, it'll diverge the path of the thing that you threw through it. So it assumes that Thomson's plum pudding model is porous, or at least maybe not necessarily porous, but at least kind of some material, something, and we don't know exactly how it's structured. But let's take a helium nucleus called an alpha particle, and we'll take that alpha particle and send it through the gold nucleus. Now here was the expectation. The expectation was that as the helium nuclei went through, they would be gently redirected by the distribution of electrons inside of there, because it's been known that by the interactions of cathode rays and again alpha particles, that they actually interact and they can redirect each other's paths. So what happens is that you send the alpha particle through the gold foil and see how it gets bent around, and that gives you the structure of the electrons inside there, because the gold must be the gold, right? It just must be whatever it is. And nicely enough, gold does not do much reaction. It's not heavily reactive, and it's very, very thin. So here's what Rutherford found. He found that most of the alpha particles went straight through the gold foil and were detected on a silver iodide screen on the far side. But just to be careful, Rutherford put a screen all the way around it, and he found out that a significant number a significant number actually bounced back. So that's kind of weird. So you throw something at something very, very thin that's supposed to allow things to pass through, but instead it bounces off of something. So that meant that if with Rutherford's concept, then he had to reconfigure what he meant by the atom. And he said, wait, there must be some dense, heavy thing that the alpha particle's knocking off of. Because if you then say, let's say you have the protons or the alpha particles are part of the gold nucleus. If you send one alpha particle into the other, they're going to hit off of each other, but they won't necessarily bounce straight off of each other. They have to be a perfect alignment for them to do that. But what happened is that the gold foil reflected off of the alpha particles reflected off of the gold foil, coming back towards the emitter. And that, as Rutherford said, was like taking a 15-inch shell, an artillery shell, such as might have been used in, say, the First World War, right around 1911, which you're talking about, 1911, and the 15-inch shell going through a piece of tissue paper, and the tissue paper bounces the artillery shell off of it. Now that would be surprising. And that's in fact, that the energetics of that are about as surprising as what Rutherford discovered with this experiment, which meant that there must be some massive object in the atom that can reflect something, can push something back, that's coming into it at high speed, that has some decent mass to it. So he reconfigured the concept to say that at the center of the atom was a positively charged nucleus, and that positively charged nucleus has mass, as most of the mass of the atom, and the electrons are somehow spiraling around it. So that is the difference between the plum pudding model and Rutherford's swarm of electrons around a nucleus. And this was put to bed Thomson's model of the plum pudding. So now we have this concept that there must be a dense nucleus. This led to some problems, though, because if it's smoothly distributed, then it can be electrically neutral. But if Rutherford's concept is right, now you've got this positive charge thing, and you've got these negative charge things flying around it, and observationally, experimentally, there is some large positive charge thing, and the electrons are negatively charged, and they're clearly not on top of it. They're near it, but not on top of it. So the question then becomes, why doesn't the electron spiral down from its orbit around this nucleus and fall into the nucleus and become Thomson's plum pudding? What is the thing that makes the plum pudding not true? Meaning it should just spiral together so it's all neutral and everybody's on top of each other. Why do the electrons stay away from the nucleus, which is positively charged. We get why it should be near, because there's an attractive force. But why should all of a sudden it stop? And nobody knew why that would be. So no matter what, when you did this experiment, you found that the nucleus had to be there separate from the electrons. And this became the topic for an enormous amount of research, and it spurred the entire idea because Rutherford's atom has a very difficult time explaining the spectra of light. Because now we have to say, well, Rutherford's atom says if you have an electron spiraling around, as it spirals, it should emit a continuous spectrum of light, not a discrete spectrum. So Rutherford's atom cannot predict the spectrum. However, it does predict the event of collisions into it, and it does disprove the plum pudding model. So there's a bit of a problem. And that problem is one experiment shows one thing, but other experiments demand that that's not the full story. And the full story of what happens to Rutherford's atom comes up next time when we talk about the Bohr model of the atom. And we'll see you soon.